Hello everyone. Today we'll talk about polarization, mainly the introduction of polarization, birefringence and Nicol prism. Introduction to polarization. Optical phenomena such as interference and diffraction cannot explain the nature of light wave, whether it is longitudinal or transverse, or even the direction of vibrations of light waves, whether they are linear or circular. What is polarization exactly? The phenomenon of asymmetry of vibrations of light waves about the direction of propagation is called polarization. When unpolarized light is incident normally on a pair of parallel tourmaline crystal plates P1 and P2, you can see in the diagram here, cut parallel to their crystallographic axis, the emergent light shows a variation in the intensity as P2 is rotated. So we see here these are crystals basically. The first one is called as a polarizer because it polarizes the light, and the other one is called analyzer, which analyzes the plane of the light received from polarizer. So that's the terminology we use. So the intensity is found to be maximum when the axis of P2 is parallel to that of P1 and minimum when at right angles. So as we keep rotating the P2, which is the analyzer, the light changes in intensity, and when perfectly perpendicular, when this axis is perpendicular to the axis of this one, then there is no light at the output, and minimum value when at right angles. This shows that the nature of light emerging from P1 is not symmetrical about the direction of propagation of light, but its vibrations are confined only to a single line in a plane perpendicular to the direction of propagation. Such light is called plane polarized or linearly polarized light. Next, pictorial representations of unpolarized light and linearly polarized lights. So unpolarized light is denoted as a dot in the center, and then directions going in all directions. This indicates that vibrations are in all directions. This is the unpolarized light notation. Plain polarized light or the linearly polarized light, the vibrations parallel to the plane of paper are given as this, are denoted as this, and vibrations perpendicular to the plane of paper are denoted as dots. Now, two important terminologies. What is plane of vibration? Plane of vibration is the plane containing the direction of vibration and the direction of propagation of light. Plane of polarization is the plane passing through the direction of propagation and containing no vibration or perpendicular to the plane of vibration. What is optic axis? Optic axis is a line passing through any one of the blunt corners and making equal angles with the three faces which meet there is the direction of the optic axis of the crystal. Optic axis is a direction and not a line. Any line parallel to the optic axis may be considered as optic axis. So you see here, this is principal section of a calcite crystal chopped, and this is the principal section. You will have to remember these angles. This is 109 degrees and this is 71 degrees. This is called the principal section, and optic axis you see here is this line. This is what is called optic axis. What is principal section? It is a plane containing the optic axis and perpendicular to a pair of opposite faces of the crystal for that pair of faces. So it is the principal section of the crystal for that pair of faces. But there may be several principal sections passing through any point inside the crystal, one corresponding to each pair of opposite faces. So say a crystal has 6 faces, so there will be one principal section per 2 opposite faces. So that means there will be 3 principal sections. Next, what are called doubly refracting crystals. As the name suggests, there are certain crystals which split a ray of light incident upon them into two refracted lights. This is very important. Such crystals are called doubly refracting crystals. Now, doubly refracting crystals are further divided into two types: uniaxial crystals and biaxial crystals. In uniaxial crystals, there is one direction called the optic axis, along which the two refracted rays travel with the same velocity. The examples of such crystals are calcite, tourmaline, and quartz. Types of uniaxial crystals. Now, there are two categories of uniaxial crystals also, and we'll be dealing in polarization with the uniaxial crystals only. So there are positive uniaxial crystals wherein velocity of O ray V naught is more than the velocity of E ray. As we just now said that doubly refracting crystals divide the light into two refracted components. The one component is called ordinary ray, another component is called extraordinary ray. So velocity of O ray is more than the velocity of E ray within positive crystals. So also we can say mu naught, the refractive index for the O ray is less than refractive index for the E ray. Example of such a positive uniaxial crystal is quartz crystal. What are negative uniaxial crystals? Exactly opposite, wherein V naught, velocity of O ray, is less than the velocity of E ray. Those crystals are called negative uniaxial crystals, which are also characterized by mu naught is greater than mu E. Example of such a crystal is calcite crystal. What are biaxial crystals? Biaxial crystals are the ones with two optic axes. Examples are topaz and aragonite. Now this is the diagram for calcite crystal. You see optic axis here, and this is the typical cell for calcite crystal. Now, once we know what are doubly refracting crystals, what are these two refracted components, E ray and O ray, now we need to talk about what is exactly birefringence, or also called double refraction. So this phenomena has to be studied well. Now, when a ray of unpolarized light is incident on a calcite or quartz crystal, it splits up into two refracted rays. This phenomenon is called double refraction. One of these two refracted rays is found to obey the laws of refraction, that is, it always lies in the plane of incidence and its velocity in the crystal is same in all directions. This ray is called ordinary ray. Its refractive index is mu naught, which is equal to sin I by sin R1. I is the angle of incidence and R1 is the angle of refraction for O ray. The other refracted ray does not obey the laws of refraction. It is called extraordinary ray. It travels in the crystal with different speeds in different direction. That is the characteristic of extraordinary ray. Its refractive index is given as mu E equal to sin I by sin R2. However, along the optic axis, both the rays have the same velocity and hence same refractive index. So you see here, this is the diagram which is important when we are discussing birefringence or the double refraction. Unpolarized light passes through the crystal. This is the principal section shown here, principal section of the calcite crystal, and the unpolarized light gets divided into two plane polarized lights. One is called E ray and one is called O ray. This is the diagram explaining the double refraction. Next, once we understand what is birefringence or double refraction, we need to understand what is Nicol prism. Now, Nicol prism is a optical device made from a calcite crystal for producing and analyzing plane polarized light with the help of the phenomenon of total internal reflection. We all are aware of what is TIR. Now, Nicol prism is a device made from calcite crystal. So, this is the construction. The calcite crystal is cut apart along the plane perpendicular to the principal section as well as to the end faces. They are then cemented together with a liquid called Canada balsam, which is a transparent glue with refractive index mu Cb, such that mu Cb lies in between E ray and O rays refractive indices. So you see here, this is very important. Mu E value is 1.48 and mu of Cb is 1.55, mu O is 1.66. So the unpolarized ray, in the diagram you can see, unpolarized ray entering the Nicol prism suffers double refraction and splits into two plane polarized lights, E ray and O ray. You see here, unpolarized light gets split into the calcite crystal. It goes here, this is the E ray and this one is the O ray. Now the O ray suffers TIR as it is going from calcite to balsam layer or from the denser to the rarer medium. So that is where the TIR comes into picture. When the angle of incidence at the calcite balsam surface, that is this surface, for the O ray is greater than the critical angle, which is theta equal to 69 degrees. Now this condition has to be met, then the O ray suffers TIR and is separated out. However, E ray does not suffer TIR and gets transmitted through the prism with vibrations in the principal plane. Thus, the Nicol prism works as polarizer. So you see here, E ray has gone out and O ray has been separated. That is taken out from the Nicol prism, and E ray is the one which we are interested in. Now, what are the applications of Nicol prism? As I said earlier, Nicol prism can be used as a polarizer and analyzer. We have seen how it is used as a polarizer just now in the previous case. The Nicol prisms P and A are called polarizer and analyzer. So just see here, in the polarizer mode, the O ray is separated out and E ray is at the output, and again it goes through the Nicol prism, which is placed in such a way that these axes are parallel to each other. Now once we start rotating the Nicol prism A, which is the analyzer, so we keep rotating it and we get no light after some time. There is no light coming out here, see, in this case. So at different positions, you see, by rotating the Nicol prism A, you can manipulate or control the intensity at the output. Now, how is this intensity connected, by the way? Now, intensity is connected as I is equal to I naught cos square theta. That is called the Malus law, where I naught is the incident intensity and theta is the angle with which analyzer is rotating. So I is the intensity coming out here.